On Tuesday, a 15-year-old boy in Magnolia, Texas, walked toward the edge of a flooded retention pond. It was the kind of basin that exists by the thousands across the suburban edges of Houston. A graded depression, a culvert, a sheet of brown water that had risen quietly over a chain-link fence. He did not resurface. Search crews eventually located his body 300 miles to the west in Bandera County, northwest of San Antonio. Another casualty occurred in floodwater the same way moving water always claims lives. Not through a wall of wind or a collapsing roof, but within a few feet of moving water across a road that appeared, for one fatal second, negotiable. Hold those two fatalities in your mind, because this is the fundamental reality that must be established before analyzing this system any further. The storm that claimed those two lives was not, at that moment, a hurricane. It was not even officially a designated tropical storm. Its strongest sustained winds, at their absolute peak, would top out at 45 miles per hour. That is a velocity you could survive standing in your front yard, a metric weaker than a standard thunderstorm gust on an ordinary summer afternoon. Yet 45 miles per hour has already resulted in 2 documented deaths in Texas. This is Tropical Storm Arthur. It earned its name today, June 17, 26, as the first named system of the Atlantic hurricane season, developing before the calendar index of the season is even 3 weeks old. Everything your instinct dictates about how to perceive atmospheric danger is about to be inverted. The primary hazard here is not the wind. The kinetic energy is an afterthought. The structural threat is the water, and the hydrological cycle of this storm has barely initiated. Consider the systemic question that remains open for investigation. When the National Hurricane Center classifies a system as weak, when they label it short-lived, when they issue a final advisory and downgrade it to a post-tropical remnant, does that signify structural termination? Or is the most dangerous phase of a waterlogged storm the precise phase that initiates after public monitoring ceases? By fully deconstructing this system, the data will demonstrate exactly why an atmospheric disturbance too weak to destabilize a patio umbrella can drown populations 48 hours after its wind field collapses. Weakening and post-tropical are two of the most deceptive terms in operational meteorology. To understand Arthur, the timeline of the past 72 hours must be reconstructed because chronological sequence dictates the physics of this event. In a standard mid-June baseline, the Atlantic basin remains quiet. The official season opens June 1st, but historical climatology dictates that the Atlantic typically does not generate its first named storm until late June or well into July. The deep tropical mechanisms that construct major hurricanes, the warm thermal core, the African easterly wave train, and low vertical wind shear are rarely assembled this early. June systems, when they manifest, are typically homegrown, disorganized Gulf of Mexico disturbances, minor architectural nuisances rather than structural monsters. On paper, Arthur fits this exact profile, a 45-mile-per-hour disorganized convective cluster that the National Hurricane Center explicitly predicted would be short-lived and dissolve within 24 hours of formation. The director of the National Hurricane Center stated clearly in a public briefing that this is not the type of major hurricane the Gulf Coast historically fears. Every component of that statement is factually accurate. Yet this system, prior to receiving an official designation, before it was ever classified as Arthur, had already been discharging heavy precipitation across Texas for days. It did not originate in the open Atlantic, nor did it initially ignite in the Gulf. Its structural genesis is highly anomalous. The critical factor is its operational behavior upon arrival. It stalled against an inland frontal boundary and became stationary. For days, it functioned as an uncategorized, unnamed meteorological engine, pumping vast corridors of tropical moisture northward into the Texas landmass. By the time the Hurricane Center assigned its initial designation as potential Tropical Cyclone 1 late Tuesday morning on June 16th, Central Texas had already entered a state of hydrological deficit, overwhelmed by 2 days of continuous precipitation. Waco recorded nearly 3 inches within a matter of hours. Camp Mabry in Austin broke a daily rainfall record for June 15th that had stood since 1964. Over 100 low-water crossings were forced to close across the Austin metropolitan area. A driver in South Austin was swept away by moving water, an RV park required emergency evacuation, and an individual near Midway High School was forced to ascend a tree to escape rising waters before emergency rescue could arrive. This systemic load was extracted from Texas before the storm possessed an official name. South of the border, the identical precursor anomaly inflicted severe structural damage across northeastern Mexico. In the state of Veracruz, more than a dozen municipalities reported extensive flooding. Dozens of landslides occurred across the terrain, and one specific municipality adjacent to an arroyo lost more residential structures to water intrusion than any other. In Coahuila, data indicated over 5 inches of rainfall within a localized 2-hour window, causing rivers to breach their banks and flood the city of Piedras Negras. In another Mexican municipality, the mayor reported that 70 to 80% of the local road infrastructure suffered direct damage from the precipitation. All of these systemic failures occurred before the system was classified as Tropical Storm Arthur. The meteorological designation arrived last. The hydrological mass arrived first. Evaluate the sequence of this crisis. The fatalities, the water rescues, the broken records, and the landslides occurred before the system reached named status. The classification chased the catastrophe. It did not forecast it. To comprehend Arthur, you must cease evaluating the storm as a localized entity defined by a center and a wind category. It must be analyzed as a geophysical mechanism composed almost entirely of water, which introduces the precise mechanical origin of this anomaly. To understand why Arthur is structurally saturated with water, we must examine an anomalous piece of tracking data that remains invisible on standard radar. Part of this storm originated in the Pacific Ocean, on the opposite side of the continent, operating as a completely separate system with an entirely different designation. Days before Texas detected any signal of this disturbance, an organized system named Tropical Storm Cristina was spinning in the eastern Pacific off the coast of Central America. Climatological models predicted Cristina would dissipate over open ocean without ever threatening the United States mainland, as the Pacific and Atlantic basins are typically isolated weather systems divided by the high topography of the Central American mountain ranges. However, when Cristina collapsed as an organized cyclone, its massive reservoir of tropical moisture did not dissipate. This moisture migrated northeast across the narrow land bridge of Central America and re-emerged over the exceptionally warm waters of the Bay of Campeche in the southern Gulf of Mexico. On June 12th, this Pacific leftover encountered a second mechanical component, a westward-moving tropical wave that had traveled thousands of miles across the Atlantic after rolling off the coast of Africa. The structural intersection of a dying Pacific storm and an Atlantic tropical wave over the Gulf initiated a messy genesis process. The African wave acted as the primary structural seed, while the remnants of Cristina provided an immediate injection of high-density moisture. This was not a textbook cyclone developing over open water. It was a collision of atmospheric remnants assembled from 2 distinct oceans, stitched together over the warmest sea surface temperatures in the basin. Consequently, Arthur was entirely full of water before it ever achieved a low-pressure center. A standard hurricane requires days or weeks over open ocean to organize its wind field before approaching a landmass, whereas Arthur dumped its moisture across northeastern Mexico and southern Texas for a week before earning a name. The system rained first and formed its structure last. The chronological timeline inverts all conventional emergency expectations. Society is trained to look for a storm that forms, strengthens, makes landfall, and then discharges rain. Arthur discharged rain, stabilized its inland position, formed a consolidated core, and was officially named while already sitting over the continent. The designation was merely a bureaucratic acknowledgement of an ongoing hydrological disaster. This genealogy contains a specific physical process known in scientific literature as the brown ocean effect. Normally, a tropical system requires a continuous supply of warm ocean water to maintain its internal engine. Once cut off from the sea and driven inland over dry terrain, the storm suffers rapid friction-induced decay and starves. However, documented meteorological research confirms that intensely saturated, waterlogged soil, the exact type of coastal marsh and soaked terrain currently covering the Deep South, can mimic the physical properties of a warm ocean. The swampy ground releases latent heat and moisture to the atmosphere, just like the sea surface. A system that should rapidly weaken over land can instead maintain its structural integrity, or even intensify its rainfall rates because the ground beneath it functions as a shallow, warm extension of the Gulf. Because of its own precursor rainfall, Arthur effectively laid down its own thermal fuel grid ahead of its path. This brings us directly to the single numerical value that masks the true lethality of this system: 45 miles per hour. This peak wind speed is a dangerously low index, hiding a massive volume of water. On a structurally healthy, category-ranked hurricane, atmospheric energy is highly concentrated around a tight core, forming a violent eye wall where the maximum hazards reside. Once that eye passes a coordinate, the primary threat terminates. Arthur operates on the exact opposite structural layout. High-altitude vertical wind shear has been actively tearing at Arthur's circulation from its inception, acting like a severe crosswind on a campfire by displacing heat away from the primary fuel source. This shear prevents the storm from stacking vertically into an efficient kinetic engine. Yet, while shear deconstructs the wind field, it does not diminish the moisture volume, it spreads it out. The convective rain bands are displaced hundreds of miles away from the weak, disorganized center, causing the rain threat to sprawl across multiple states. 16 million people were placed under flood watches from South Texas to central Mississippi, a hazard footprint that was subsequently extended east into South Georgia. This massive cloud shield is the true storm, not the geographical dot on the map labeled Arthur. The threat is defined by spatial footprint and forward velocity, not a localized eye. A 45-mile-per-hour wind field cannot compromise building integrity, but it can park a fire hose of Gulf moisture directly over a single watershed for 3 consecutive days while moving at the speed of a bicycle. The wind is weak, but the water is patient, and operational history proves that structural patience in a flood zone is what drives the final body count. To understand how a slow-moving storm transforms ordinary precipitation into an absolute catastrophe, we must analyze the arithmetic of slow. A storm's total accumulated rainfall at any single point on the ground is dictated by 2 variables: how hard it is raining and how long that rain stays over that specific coordinate. Rate times duration is the governing equation. A fast-moving tropical system, racing along at 25 or 30 miles per hour, dumps its water and exits, meaning even heavy downpours remain survivable because the soil, storm drains, and local creeks can evacuate the volume roughly as fast as it arrives. Arthur, conversely, has been crawling across the landscape at approximately 9 miles per hour, barely faster than a casual bicycle ride. If a moisture-loaded tropical band produces 2 inches of rain an hour and it becomes stationary because the larger steering currents have collapsed, the duration variable climbs continuously. 2 inches an hour for 2 hours is 4 inches, which is an inconvenience. 2 inches an hour for 8 hours is 16 inches, which is an architectural disaster. The rainfall rate remains identical, only the clock changes. This mechanical slowdown is amplified by a geometric phenomenon known as training, where individual rain bands line up like rail cars on a track, passing one after another over the exact same point. It is not that a single cloud sits still until it empties, but rather that an assembly line of new clouds continuously forms upwind and rides the identical path downwind over one unlucky watershed. This geometry explains why a 15-inch rainfall total can manifest a mere 10 miles away from a location that received only 3 inches from the same storm. This structural dynamic produces widespread regional forecasts of 5 to 10 inches, punctuated by isolated bullseyes approaching 15 to 20 inches. These catastrophic bullseyes are not determined by the storm's wind category, but by micro-variables of terrain and the alignment of rain bands, meaning the worst flooding from Arthur can occur tens of miles away from the official track. On the coast, this freshwater deluge collides with a second water threat coming from the sea: storm surge. Surge is not a series of waves riding on top of the water, but a bulk rise of the entire sea surface driven by the storm's winds, physically piling ocean water against the coast and shoving it inland on top of the normal tide. Arthur is forecast to drive a surge of 2 to 4 feet from Port Bolivar, Texas, eastward to Morgan City, Louisiana, with the worst impacts concentrated on the eastern, right-hand side of the track. Because tropical systems in the northern hemisphere spin counterclockwise, the wind on the right side blows in the same direction the storm is moving, compounding the force pushing water onto the shoreline. While a 2 to 4 foot surge sounds modest, it is sufficient to inundate low-lying coastal roads, push saltwater into marsh communities, and float vehicles. The upper Texas and Louisiana coast is a fractal edge of bays, bayous, and barrier islands connected to the mainland by single roads. A 4-foot rise does not need to submerge a house to be lethal. It only needs to cover the sole evacuation route out at the exact moment freshwater flooding begins building behind it from the rain. When this occurs, the land's drainage has nowhere to go. Gravity can no longer carry the fresh water downhill to the Gulf because the storm surge has raised the level of the sea, causing rivers and storm drains to fight against a wall of seawater pushing in the opposite direction. This is compound flooding, where rain and surge stack on top of each other. This physical gridlock turns coastal Louisiana, with its low elevation and absolute dependence on mechanical pumps, into the most vulnerable ground in this entire event. Large sections of southern Louisiana sit below or barely above sea level, remaining dry on an ordinary day only because pumps lift water over levees and out. These pumps have a strict operational ceiling on how many inches per hour they can move. When rainfall outpaces pump capacity while the surge simultaneously raises the height they must lift the water to, the mathematics of the system fails completely. The water spreads sideways through flat, interconnected bayous with almost no gradient, sitting on the landscape for days. This specific combination of below sea level elevation, pump thresholds, and backed-up outflows is precisely why emergency officials in several southeast Louisiana parishes changed their language from advisory to imperative, issuing proactive evacuation orders to escape a lethal trap before the heaviest rain even arrived. Executing a proactive evacuation order under deep uncertainty is an immense operational and psychological challenge. Local officials must issue these directives based purely on probabilities, acting against a storm that public headlines are simultaneously downplaying as weak. A parish official must stand before cameras and instruct residents to disrupt their lives and abandon property for a 45-mile-per-hour system, knowing that if the storm fizzles, they will be mocked for overreacting. Yet they issue the warning anyway, because the gap between the public perception of a minor storm and the operational reality of a life-threatening flood is precisely where fatalities cluster. This systemic mismatch is complicated by the false alarm tax, where every precautionary evacuation that does not end in disaster erodes future compliance, conditioning the population to ignore the next critical warning. In Texas, this structural hazard forced the governor to declare a state of emergency covering 101 counties, activating 24-hour emergency operations statewide for a system with minor winds. New Orleans Mayor Helena Moreno demonstrated identical institutional caution, aggressively preparing rescue boats and barricades in flood-prone zones well before the heaviest rain bands materialized. The professionals consistently size their response to the water volume, not the wind speed, because the Gulf Coast has already learned this lesson in blood. The underlying engine of this vulnerability is pure thermodynamics. Arthur formed over water running above 83.5 degrees Fahrenheit off the Texas coast, which translates to a heavily loaded atmospheric gas tank. Under the Clausius-Clapeyron relationship, every single degree Celsius of atmospheric warming enables the air to hold approximately 7% more water vapor. When a system organizes over an unusually warm Gulf, the ceiling on its maximum potential rainfall rises exponentially. When this high-volume moisture tank pairs with a complete collapse of atmospheric steering currents, a slow, stationary rain factory is generated. Historical data indicates that the baseline warmth of the Gulf has quadrupled its departure from normal over the last 2 decades, particularly following a regime change after the record-strength 2015-26 Super El Niño. While seasonal forecasts from agencies like NOAA predicted a near-normal or below-normal season of 9 to 13 named storms due to wind shear from a developing El Niño pattern, this data point hides a dangerous trap. Total storm count is a measure of quantity, telling you how many times the dice are rolled, but ocean warmth dictates how heavily loaded each individual die is. A quiet season can still produce a catastrophic flood because the thermal energy of the water raises the ceiling on how much water a single, weak system can carry. The physical blueprint for this exact disaster scenario was drawn in August of 2017 by Hurricane Harvey. While Harvey made landfall as a major Category 4 system, its steering currents collapsed immediately upon crossing the coastline. The winds rapidly degraded, but the water became a historic disaster engine, sitting stationary over southeastern Texas for 4 consecutive days. Harvey delivered localized rainfall totals exceeding 60 inches. 5 feet of water fell from the sky onto a flat, urbanized coastal plain, dumping trillions of gallons of water with such immense physical mass that geophysicists documented the Earth's crust physically sinking by 2 centimeters under the weight before the land rebounded. This record-breaking destruction occurred long after Harvey's winds collapsed below hurricane and tropical storm thresholds. Families who assumed they were safe because the kinetic wind threat had ended found themselves trapped by a quiet, relentless, rising deluge that completely submerged the first floors of their homes. The vast majority of Harvey's fatalities were caused by freshwater drowning, not wind, demonstrating that wind scales are entirely unrelated to hydrological danger. If Harvey is dismissed as an isolated anomaly, the historical record provides an even more striking parallel from August of 26, a catastrophic system that never even received a name. This nameless, low-moving mass of tropical moisture stalled over southern Louisiana and dropped well over 20 inches of rain, breaching record river crests, flooding tens of thousands of homes outside high-risk zones, and causing billions of dollars in damage. This historical event proves with absolute certainty that you do not need a hurricane, a defined center, or intense winds to trigger a catastrophic flood event across the Deep South. The water does not verify the meteorological label before deciding how high to rise. To maintain analytical integrity, we must acknowledge a crucial mitigating variable. Houston, the permanent benchmark for flood vulnerability, was largely spared the worst-case scenario. This was not merely meteorological fortune, it was structural mitigation. Prior to Arthur's arrival, regional water managers deliberately lowered reservoir capacities and drained local networks, specifically at Lake Conroe and in Brazoria County. This pre-positioning created systemic volumetric room to absorb the incoming precipitation. This is the direct application of post-Harvey institutional memory, proving that infrastructural adaptation functions when accurately deployed. However, this success is highly localized and dangerously early in the timeline. Sparing a major urban center with national media attention dictates absolutely nothing about the hydrological reality of the rural watersheds immediately downstream. As Arthur tracks eastward toward Louisiana and the Florida Panhandle, the National Hurricane Center initiates its most dangerous administrative procedure, the transition of the system to a post-tropical cyclone. Wind shear has shredded the kinetic circulation, triggering a bureaucratic reclassification. The tracking cone vanishes from public broadcast, and official advisories terminate. The psychological trap closes. Society equates a post-tropical downgrade with systemic collapse. But a decaying, sheared cyclone with no tight center operates as an optimized, disorganized rain factory, spreading its fluid mass over the maximum possible surface area. The word weakening describes kinetic wind. It is entirely unrelated to hydrological volume. A civilian in western Georgia might hear the final advisory, assume the threat has terminated, and subsequently face an unexpected 10-inch localized deluge that drowns a secondary transit route. In the vacuum of public understanding, alternative narratives attempt to rationalize the event. The most pervasive is the assertion of intentional weather modification, specifically invoking ionospheric research facilities. This represents a fundamental illiteracy of geophysical energy budgets. A mature tropical system processes thermal energy on a scale that dwarfs the entire continuous electrical generating capacity of human civilization by a factor of hundreds. There is no existing technology capable of steering or seeding this mass. The second narrative categorizes the storm as unprecedented. It is not. Early season formation is a documented probability, functioning as a loaded die. A continuously warming Gulf does not script individual storms, but it structurally elevates the ceiling for extreme rainfall events. The third assertion, that the minimal wind speed proves the event was a fabrication, is instantly nullified by the confirmed fatalities. Dismissing a flood threat is a luxury, reserved exclusively for those residing outside the inundated watershed. Arthur is an atmospheric thermometer registering early-season thermal capacity. It does not dictate the total storm count for the calendar year, but it proves the basin's thermodynamic engine is primed. As the remnants push east, the system faces divergent statistical futures. The most probable outcome is a gradual fade, depositing a manageable 5 to 10 inches of widespread rain across drought-baked topsoil. Ironically, this parched soil acts as a hardened surface, repelling rather than absorbing the initial runoff. The secondary, higher-stakes probability involves a stalled frontal boundary, anchoring a training rain band over a vulnerable, unprepared municipality, generating a rapid, isolated 15-inch accumulation while spawning rain-wrapped tropical tornadoes due to low-level wind shear. The absolute ceiling of this event, the ultimate systemic limit, is a complete stagnation over an unprepared population corridor. The fundamental reality of Tropical Storm Arthur is that modern society has constructed rigid, stationary infrastructural grids beneath a fluid, expanding atmospheric ceiling. The water does not negotiate with municipal boundaries, bureaucratic wind classifications, or public fatigue. The physics of evaporation and precipitation operate on strict thermal laws. When the atmosphere is loaded with an anomalous volume of vapor, gravity will inevitably pull it back to the surface. It is merely a question of geographical alignment. Ultimately, water, gravity, and time will relentlessly test the structural limits of every artificial barrier we have engineered.